Welcome to Homework Lib.
Okay, so this problem seems like it's a bit long, and it can be, but we're going to make some simplifications to the way we approach solving this that will hopefully make things clearer and reduce the amount of tedium required. So, the basics of this question is that we have a carbon monoxide molecule, and it can vibrate and it can rotate. So, if you imagine it's attached by some spring here, then you can have some vibration where they go back and forth, and then you can have rotation, like you've maybe seen in some problems already, where they maybe rotate about their central axis here. And each one of these collective motions has a certain energy associated with it. So this is what I'm going to call ER, which is rotational energy, and then this is vibrational energy, or EV. And the problem 42.14 is asking us to consider different combinations of L and N in various transitions to see what sort of photon would be absorbed by the system if that certain transition were to occur. And thus, we're going to be looking at, we could calculate it by hand and just brute force it all, but that's a bit of a pain. So, what we're going to do is develop a bit of a notation, because all of the transitions for the vibrational states all go from n equals 0 to n equals 1. So, you know that there's going to be one standard delta EV, which in this case it's said in the text, but it's quite a high energy at 0.2690 electron volts. And this is going to be our base unit for dealing with the vibrational state changes. So refer back to this for future slides. And then we have our rotational energy, which sometimes it goes forward, sometimes it goes back. But the unit that we're going to use are units of h bar square over 2 times the moment of inertia. So I'm going to call this delta ER, because we may have differing L values, but this ER will never change. And in the case of carbon monoxide, this delta ER is 0.2395 electron volts. So don't get the units here confused. But at the end of the day, you're probably just going to put these in your calculator and then use them over and over. So both of these values came from the text, but you can calculate them if you want, because you can grab the moment of inertia or the frequency of oscillation, or calculate it if you wish. So I'm going to start jumping into the other slides, which I've already got the transitions in there. And like I said, for the in vibrational transitions, it's always going to be just delta EV. So we're not going to worry too much about it. And then for the total energy transition, I'm going to call that delta E. And at the end of it all, the answer is looking for things in terms of wavelengths of the light that's going to be produced. And if you recall, the energy of a photon being hc over lambda, thus lambda is hc over energy. So we're going to define what this delta E is, And then we're going to get a value for lambda, which will be hc over delta E. All right, now for the first one, we are going from L equals 2 to L equals 3. So we're going to have E3 minus E2, which we take 3 plus 1 minus 2, 2 plus 1. So this you get 6. Here you get 12. 12 minus 6, it's just 6. So 6 delta ERs plus 1 delta EV is equal to our total delta E. And plugging that into here, we get a wavelength of light that is 4.585 micrometers. Okay, so make sure that you understand what we did there. And this side is going to stay the same pretty much each time. However, the left part of this will be differing with the different levels. So we'll jump right in here. We're going from L equals 3 to L equals 2. So 2 times 2 plus 1 minus 3 times 3 plus 1. We already figured that out. That's 12 being subtracted from 6. So 6 minus 12 minus 6 delta E Rs plus, we see we're going from 0 to 1, so just 1 delta EV is equal to our total delta E. And our photon wavelength in this case is hc over delta E, which is a value of 4.635 micrometers. And so this wavelength is longer, which means it's slightly lower energy, which makes sense because we are actually going down in rotational bands whenever we capture this photon. So it shouldn't have as much energy as the last one. And then finally, we're doing the exact same trick here. We go from L equals 4 to L equals 3. So 3 times 3 plus 1 minus 4 times 4 plus 1. Here we have 3 times 4, which is 12. Subtracting 4 times 5, which is 20, which is minus 8 delta ERs. Add that to our 1 delta EV for the vibrational energy. And you see it's a bit tedious, but it's all exactly the same as the previous slides. So you can plug this in the Wolfram Alpha or your calculator and get that. We have a wavelength of 4.642 micrometers or micrometers. So it's pretty interesting. It's a very small difference in the last one. So you can see that the rotational bands really don't contribute much to the total energy coming out of it all.